Okay, so what you ought to do for this section is you ought to open up your book. I'm working on page 222, and you ought to open up your book, pause the video, and fill these in. You need to. It'll help you get the blood flowing. It'll help you learn it. Okay, so let me suppose that you did that. The three terms which we want to use with great facility. We want these to be comfortable. So we need to talk about them. Number one is energy, and energy is the capacity to do. What do you have? That's right. Work. Okay, energy is the capacity to do work. Work is the result of a force acting through a distance, and heat is the flow of energy caused by a temperature difference, okay? Caused by temperature difference. Okay, so energy is the capacity to do work. Work is the result of a force acting through a distance, and heat is the flow of energy. We're gonna chew on these terms a good bit now. So first of all, let's think about how these things fit together. Energy is the capacity to do work, and part of energy is potential energy. Another part of energy is kinetic energy. Well, thermal energy is like a potential energy. It's the energy associated with temperature, but it's the motion of little tiny particles called atoms and molecules, right? That's what thermal energy is, and it's generally associated with temperature, but is a kind of kinetic energy. And potential energy is the energy that's due to position or composition. Chemical energy is a potential energy also, right? Because it's associated with the positions, right? Positions of electrons and nuclei. So chemical energy is a kind of potential energy, and thermal energy is a kind of kinetic energy. That's right. So let's think about, let's review those terms. Kinetic energy is the energy due to, this is also on page, there's just a ton of terms on page 222. So I hope you've got your book out in front of you. Page 222 says kinetic energy is the energy due to motion. Thermal energy is the energy associated with temperature. Potential energy is the energy due to what? Say it out loud. It's the energy due to position or composition. Okay? And a chemical energy is the energy associated with the positions of electrons and nuclei. I realize we had this in the previous slide, but it's going to be worth it. Look at that. That's why chemical energy is a kind of potential energy. All right, so let's think of an energy to a couple different energy transformations. The first one is maybe gravitational potential energy. Can you see that this billiard ball? This is a little ball that you use for a game with a little green table. We've seen these before. So this has got energy in it because it's held above the Earth, away from the Earth, okay? It's got gravitational potential energy because it's up here, okay? If you let go of it, the gravitational potential energy gets converted to kinetic energy. Can you see that? Because this ball has motion now, right? Okay. And so it gets converted from potential energy to kinetic energy. Okay, so another energy transformation might be a mechanical potential energy, right? So this is potential energy because the ball is held down on a spring, and that is due to its position or its composition. The ball has got some energy due to its position or composition, and then when you let go, it makes motion, right? So that's kinetic energy. All right, so let's think now about two other terms that we're going to want to use here: system and surroundings. Okay, so if you've got some system, and a system, I think the book, you know what, I don't think I have that defined here in the video, but I'm going to read what a system is, okay? A system is A system is everything that we're investigating. Okay, so so Tro says on page 223, a good way to understand and track energy changes is to define the system under investigation. That's what you're investigating. The system could be the chemicals in a beaker, could be iron reacting with a hand warmer. It could be well, lots of things. It's whatever you're investigating. Okay, and the surroundings are everything else. That's everything within which everything with which the system can exchange energy. So the surroundings are going to be, if you think of the hand warmer, the hand would be the surroundings, and the warmer would be the system. Okay, now with energy transfer, it's going to be really valuable for you to appreciate that if you begin, you've got, say, 50, can you see 50% here? Whatever full is, okay? And here, what's this? About, I don't know, that's 25%, about 12.5%. Okay? If whatever energy you have between your system and your surroundings is going to be constant. So whatever the system loses, and it looked like here it lost 25%. Can you see that? And can you see it must have gained 25% here? Right? So that's what this figure is on in your book on page 224, and it's really it's emphasizing that whatever the system loses, the energy gains. Okay, the surroundings, I just said that wrong. I know I did, the energy gains. But this is correct. The surroundings gain the exact amount of energy that's lost by the system. All right. Let's look at the units of energy. So in kinetic energy, this is the formula for kinetic energy, 1/2 mv squared. The mass of an object is measured in kilograms, and the velocity is measured in meters per second. Okay? So the units are going to be, can you see this? Kilograms, meters per second squared, which is the same thing as kilograms, meters squared per second squared. Which your book is oftentimes going to say kilograms, meters squared, and it's going to say per second squared like that. Okay? And by the way, this is defined, this is the definition of a joule. A joule is a kilogram, meters squared per second squared. Okay? That's just the definition of a joule. And that's on page 224. All right, so this is real interesting, I think. So look at this. If you have a light bulb that's 100 watts, 100-watt light bulb, and you burn this for 1 hour, okay? Can you see that you are going to can you see that you're going to burn 100 watt hours? 100 watt hours is what you burn, okay? Now, this is a watt and a kilowatt. There's 1,000 watts in a watt. So this is going to be 0.1 kilowatt hours, right? Amazing, huh? It's really amazing. And it turns out that there's this many joules in a 0.1 kilowatt hour. All right, you don't need to memorize that. I just want you to look at those units and get used to them, because we're going to be using these units, and I don't want them to get in your way. I want to be helpful to you. Okay, as I said, we have calories and joules. These are going to be the primary units that we use, calories and joules. It turns out that 1 calorie is equal to 4.184 joules. And 1 kilowatt hour, we saw this on the previous slide, is that. These are considered exact, so there's an infinite number of sig figs in that number. All of these numbers, these are considered exact. I don't think I want to say anything else about that. Okay. One last table, this is real interesting on page 225. The amount, look at this. The amount required to raise temperature of 1 gram of water by 1 degree centigrade. 1 gram of water by 1 degree centigrade is 1 calorie. Right? You see that? 1 gram of water, 1 degree centigrade is 1 calorie. It's the definition of a calorie, okay? The amount And then we can just convert those out. Now watch this. The amount required to light one 100-watt light bulb for an hour, we saw that in a previous slide. It's 3.6 times 10 to the 5 joules. Now look at this. This is amazing to me. It takes almost the same amount of energy, right? 3.6 times 10 to the 5 joules to light a 100-watt light bulb for an hour as it does, look at this, for a human body to run a mile. Of course, it depends on the size of the body and such, right? But it's about the same. Can you see that? 3.6 to 4.2. They're both in the order of 10 to the 5. Amazing. Okay, and then the amount used by the average U.S. citizen in one day is about 1,000 times that, 2,000 times that. That's amazing. It's like running 2,000 miles, right? Okay. So, anyways, these are just some numbers that it's good to look at those and get a sense of what these energies mean. And I think that's it for this section.